Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. Hi, I'm Dr. Alexander NGENZI from University of Rwanda College of Science and Technology, Department of Computer and Software Engineering. Hello, good morning, dear students. Good morning, everyone. Today we are going to start a new chapter, which is a Z transform or Z transform, and we will look at some of the outlines here. Number one, we shall discuss we will have some introduction of it and have introduction. So we are going to discuss Z transform. And we will have some outlines. Number one, we are going to discuss, of course, introduction to Z transform. Number two, we are going to discuss types of Z transform. Number three, we will discuss region of convergence, also abbreviated as ROC. We also discuss about poles and zeros. Poles and zeros. Also, we shall discuss about properties of region of convergence. We will discuss about some common Z transform, some common Z transform, which means some of the popular Z transform. We discuss also inverse Z transform. And also we will have also their properties, which means Z transform properties. We will have also impulse response. And also we have convolution properties and correlations. Convolution properties and correlation. So here on the top, it will be the impulse response and convolution sum and convolution sum. So these are among the subtopics or outlines that we are going to discuss today. Of course, we shall begin with introduction. So let us just discuss what is Z transform and how does it get involved in digital signal processing. First of all, I would like to tell you that Z transform is very useful in converting signals. Of course, they are discrete signals to their corresponding frequency domain signals. But these signals are in complex values or complex numbers. They are complex numbers, you know, the complex numbers in the polar form. In any circle, we have a light and the left hand side, you have imaginary and the real numbers. Those are the complex values. So we shall look at the format. How does Z transform look like? So without taking much time, we are going to begin with number one. So we begin with the first point that we have listed here. And okay, so as I say, Z transform is used to convert the signal in discrete value of the complex numbers into their corresponding frequency domain complex values. So suppose we have a Z at the complex number. You remember, we will have for the first time we will have an exponential value of e to the power of j theta, like this. But because the circle itself will have a size, and the size will be as we said from the previous chapter, we said the size here, when we talk of signal processing, we talk of amplitude. So we are going to add amplitude A, and which is going to be Z A into E power theta. So this is when you can recall very well in the complex values and also trigonometric numbers. Trigonometric numbers, we can convert this one, and this one becomes A into bracket, because we are going to convert this. It's going to be cos theta plus j sine theta, like this. So this is when it is extended, it looks like this. Why am I saying this? Because you are going to see how the rotation of the angular rotation, be it clockwise or anti-clockwise. But in this case, it goes anti-clockwise to count from the right angle to any value. For example, here you can have a value okay, like this, but you can have also value theta at this stage. So it will go counterclockwise in this direction, and here you can dividing this. For example, this is imaginary number, and this one is real number. So it goes in this way to counter the clock, and this angle can keep on changing depending to the value. So this side is the right-sided. We are going to discuss also this right-sided portion, and also when text, this one becomes left side. Yeah, on this side. But also it can be the full, bilateral side, they just going into 360 degrees and becomes bilateral sides. So it's going to, so what's the use of this Z transform? For the first, we have seen that it is used to convert the discrete value numbers into the frequency domain. Suppose you are for example, once you are given, for example, the numbers, the signal when it is discrete form, you remember the discrete form, how it looks like, and you want to convert it into the frequency values. For example, if the system, remember here we are going to concentrate on the system itself. We are not going to concentrate on the single signal. So we want to make this one the system, from which system we will be having many signals here. So this was a little bit introduction. But there's one of the systems that we can use here in a Z transform. We can, you remember, we use a filter as a system itself to design, for example, poles and zeros. So I mean, to design some filter or low pass or low band pass filter or high pass, like so on and so forth, so that the system can filter out the noise and interferences which may come with our signal. So that is one of the notation of our signal, and we are going to see how this Z transform can help us to come up with the results. How this Z transform can be applied? Of course, you remember when it is if we can recall what we discussed last time. We discussed about the discrete time signals and the continuous time signals. And here we can call the continuous signal to be the frequency that we want. We want to convert from the signals, the signal which is discrete to their corresponding. Here, when you are converting, of course, we want to see from which side, which place can we apply all these values, and then how are they going to be useful to our systems once we want to convert any signal from either. I shall tell you also that it is also possible to convert the continuous signal to their corresponding discrete time. So now we are going to see, we have seen its a definition of what it means to be a Z transform. And here we are going to see where does it get applied. Where does it apply in real scenarios? So we are going to see the application. Number one is going to be, it is going to describe the discrete signal in their corresponding system. So as I mentioned, it's going to be a pure discrete signal or time signals in their systems. It's going to be used to analyze the degree of stability, to analyze or analysis of the degree of stability in the system. Stability in the system. Those are the stability of discrete time system. Stability of the discrete time systems. It is also going to be applied to analyze the quantization of errors. Suppose if the signal has come with the errors, and you want to make it free from noise, interference, crosstalks, distortions, and so on and so forth, you will have to indicate or to quantize the signal to its the purest form. We want to put it to analyze the quantization errors which may come with the signal or noise or any interference in digital filters. It's also going to compute the frequency response of discrete time. So also to compute the frequency or response of their discrete time systems. Of the discrete time systems. So these are the applications where we can find Z transform, where it is applied. And most of the cases here, what we are intended to get is what is our main goal, or what is our main target, is to get rid of all those noise or the errors that may come with the system itself or the signal itself. Then we get a pure signal which will help us in our communication. So those are some of the applications. Now we are going to discuss the format, the way how Z transform looks like. So we are going to see how does it look in terms of calculation or computations, as we have seen, and what are the definitions of each portion of the format of the equation. Here we are going to see when you are converting a signal from discrete value, we are going to show, for example, if the signal is in discrete value, it's the one which is going to be computed. Therefore, in the other hand, it's going to be the frequency. Now we are going to look the frequency domain of the bilateral Z transform, or two-sided. It can be bilateral domain, or Z transform, or two-sided value. So there are, before we began this chapter, if you can recall very well from the previous chapter, I talked about the double-sided, the single-sided, and so on and so forth. So, or you can say bilateral or unilateral, saying this is bi means two, and un means one. So now we have very, very important. Previously, when we were just doing the discrete value signals, we used to discuss, for example, x of n. Like this. So this demonstrates the discrete value that you are looking for. But here we are going to make a very big X. Of course, it is with respect to Z, and it's going to be double. Double means from negative infinity to infinity. There is no positive infinity, of course. It's a negative infinity to infinity. Why does it? Why do we call it a double? Because if you can, there are two steps that determines why it is double. So you get from negative infinity to 0, for example, and then from 0 to negative infinity. You can see they are two double-sided. Also, on the z form or polar form, we have seen the left and the right-sided. So once they are combined from negative, from positive negative infinity to positive infinity, that is clockwise direction, then it becomes. So the summation here is going to be. You can call it, for example, you can say z. Of course, with respect to x of n, here is going to be okay, let me put summation from n, of course we are talking about n equals to infinity of the x values x of n, and then it's going to be with respect of z power n. So this is the general formula to calculate bilateral. So this is a general formula, of course, for all z transform if you want to convert the values. So here I wanted to mean, for example, x of z is going to be big summation from n, which is equal to negative infinity to infinity of x of n, then z power negative n. So this is the general formula of our double bilateral or double-sided or two-sided. So it's going to be double-sided or two-sided. So in every calculation of us, just coming from negative infinity to infinity is going to be written in this form. So you can master this. This is very important in terms of calculations. You understand? So these values we are going to, we said z can be presented in the way, the form I showed you from the beginning. Of course, we will be having some complex numbers, and n is the value, the normal value of discrete value that we are going to determine. So let me show you how we can compute, come up with the general form of unilateral or single-sided. Now number two is going to be the single. Number two is going to be unilateral or single-sided or one-sided. So I told you when you are coming from negative infinity to positive infinity, you will have one step from negative infinity to 0, then from 0 to positive infinity. So here it's going to begin from 0. So x of z is going to be, you can put the other one or not, but the general form here is going to be summation from n is equal to 0, n is equal to 0, I tell you, then to infinity of x, this is small x of n, z power n. So this is a single-sided or double-sided. So throughout our calculation, we are going to use these formulas, and we will have. So it can be single-sided. When we talk of single-sided, we are talking of right-sided. Remember when I was dividing this circle into two pieces, we said this is right side and this is left side. So it was coming from this end to the other end. So from 0 to infinity, then from 0 to negative infinity. So from here to the whole circle becomes bilateral, and then from this point or from this can be any value from 0 to infinity. So we are talking about this graph. Okay, so this, if we here calculate using single-sided, or you can even determine the value when you see where the equation lies, or how many numbers you are going to calculate, depending to which number you have, whether it is beginning from infinity to negative infinity. So these are considered one of the main types of calculations that we are using. So now we are through from the outline of types. So remember, we began with introduction. We have talked about the types of Z transform. Mainly these. The information that we use are these ones that you can see. So let us just begin with our next points. So we are discussing point by point. So any question you will have to write to me, and I'll give you the full explanation, or you can email me on the other emails that I gave you, so that you can get the full package. So here we are going to discuss about the region of convergence. Now it's going to be I think it's going to be number 3 of the outlines. Remember, we are talking about region of convergences. Okay, what's the region of convergence? So they converge in the real examples. There is diverge and converge. So you are separating, or you are uniting or joining. In this case, the joining here, or summation of any sets of values of signal of Z, they are the ones that we call region of convergences. And here, for example, if I can draw the other circle, and then from the center, I can have so many cycles here, having zeros and poles and zeros. Remember, the zeros are the numerator of the fractional, and the poles are seen at the denominator. So the numerator is going to be zeros. We shall discuss about this one. But what I want to say, you can determine which pole are here at any particular point, or here, or any point here. So you decide which inner cycle is going to be. So the convergence area of, for example, the first circle can be this side, because there is external and inner convergence, or single or double, depending to what we have seen there. So it will go to be enclosed in the circle itself, and that one is going to be, or remember, when you want to show something which is enclosed, you remember you have to do a modulus of that value. Then, for example, you can say x of n merged to this extent. For example, big X of Z can be of this cross, of this side. So you get out there, you convert those sides. So the values were enclosed in this domain. So it's going to the finite value. The values are countable. You can count them. They are not infinite, I mean the infinite values. You remember the finite values are the ones which can be counted, and the other one cannot be counted. So it's going to attain the values of z which are counted. Values, the values have to be finite or defined or counted. So from the very long signal, which may have the infinite values, we are going to purify them and to make them ready to be counted and at each stage given the time of the signal. And also it can be calculated, for example, using algebraic expression and any other terminologies. But most of the cases here, when when there are numerous signal in one signal, then because it is complex. Being complex, meaning it has multiple signals. Then these signals can be algebraic expressions which need to be purified. For example, the equation here that we are going to use here is general or generic equation that we are going to use. For example, region of convergence, for example, having any boundary, as I told you, can be of, for example, a z of x of n, which ranges from summation of n. This is double-sided. Remember, double-sided looks like that. Then x of n z power negative a, and that one where it is less than negative infinity, for example, then you enclose. So any value obtained here is going to be converted in those values. There is going to be enclosed in those values. So however much the signal is going to be complex, it can be divided in any case to a simplified form. And that is the beauty of having this Z transform. So you can see here you can have multiple signals, but also it's going to be simplified by a region of convergence. So this I explained this one, this cycle having this value, and then we have this signal which is theta varying to this side, and this is what we call, for example, Z plane, which is going to have imaginary values here as y-axis, and then real numbers here, or you can write the real numbers here at x-axis. And this theta can be termed as the frequency in this case, because we want to convert the values into their corresponding frequency values. So we want to, we no longer need all these angular, we convert them, and remember the frequency in their conversion is 1 over t. And suppose if you have time period, then you can either this one, make this one. Also, you can just put it in terms of theta, for example, 2 pi over t in that case. So that's why here they are mentioning, instead of just saying theta, they just talk about the frequency. This is going to be frequency. So this is called unit circle. Unit circle, and of course this is a Z plane. It's going to be a Z plane. Yeah, and this is a the unit circle means 1. It's a 1 that rotates at its point as 1, for example here. So you can put it. That's why it is called unit circle. So that's how we can present this one. I hope you get the point. So here also we discuss. We are going to see to talk about their properties, the property of the region of convergences. So before that, we can have an example. For example, suppose if you are given a signal in this form, x of n, which is 0.5 power n, u of n, like this. Then they say you calculate the poles and zeros. For example, if you want to get the poles and zeros, so you can recall the equation in the table that maybe you shall see when you get the content of my notes or the handouts. It's going to be the table that shows at which particular interval you can get. And this one also is similar to the corresponding values in the Laplace transform, which the Laplace, of course, you remember the history is one of the French scientists that invented or discovered these values of Laplace that are used for continuous signals in a frequency domain of the signal processing. So in this case, we are going to see some of the tables. But here we have the corresponding value where we can say summation of n, of a single-sided, for example, n is equal to 0 to infinity of a power n. So if you want to compare that one in a Z transform manner, you can have its equivalent is 1 over 1 minus a, from where the modulus a is going to be less than 1. So in this case, so this one also can be calculated in the same way. So in this case, where it is the a, we are going to replace it with z, so that you can get information from. So if you can compute from, for example, x of z is going to be summation of n equals to negative infinity of infinity small x of n z power n. And in this case, you can substitute some of the values because this is going to be single-sided, and you get, for example, the value here. You can get the value here, which is, for example, you substitute the values in here, then it's going to be x of z is going to be summation of n is equal to 0, because it's going to be one-sided, of infinity to infinity of our function, which is this. So our x of n corresponds to this. So we are going to take 0.5, then we power n, 10 times z power negative n. And this is going to be nothing but 1 1 over, it's going to be 1 over, when you compare the other formula, it's going to be 1 over 0.5 z power negative 1, and which can be converted, for example, which is going to be z if you multiply by z all sides, or multiply by z all sides, it's going to be z minus 0.5, and here you can easily determine the poles and zeros. So if you can see